Okay, hello. Welcome to this presentation of the scientific paper, and the title is TSO-DSO Performance Considering Volt-Var Control at Smart Inverters. And the study case is Vestfold and Telemark in Norway. This paper has been the collaboration between members of the University of Southeastern Norway, University of the Nuevo León in Mexico, and of course the University of Osijek. And let's start with a short introduction. And as you must be aware, power systems are changing, and one of the areas that changes are going extremely fast is at distribution level. Distribution level must change a lot in order to cope with the new characteristic of the demand side. And as a consequence, the distribution system operator must take the advantages of the consumer installing low carbon technologies and the market possibilities of compensating the customer for offering services to the grid. As a consequence, the DSO must change and use the approach of new customer-centered active distribution network. The good news is that the power electronic interface that is used for low carbon technology, they are very versatile, and they are offering very excellent mechanism to offer controllability features to the DSO. And as a consequence, the modern power electronic interface, they have the possibility of playing a crucial role in frequency and voltage control in the active distribution network. And the IEEE standard, the 1547 in 2000, from 2018, has created a new tendency inside the power sector, and that is the term smart inverter. Smart inverter is basically a power electronic converter that has several features in order to enhance the performance of the distribution system. And this IEEE 1547 is enable the prosumer to offer services to the DSO, and as consequence, the DSO can offer those services to the TSO. What is true is that today we can think about the distribution system like a cluster of microgrids that they can provide services now to to the to the system. It includes services like congestion management and voltage support and balancing services and so on. And what is in this paper, we are very focused. We are focused in the Volt-Var control. I mean, voltage and reactive power control provided by smart inverters, considering the new definition of performance, enhancing the performance of the TSO-DSO interaction. Okay, in this paper, the assessment is basically focused in two main variables. One of them is the total energy losses in the system, and the other one is the voltage profile between the DSO and TSO. In this case, in this paper, we are using a numerical assessment, using numerical simulations based on the excellent power factory, and the test system that we are using is basically a regional electrical system in the southeastern Norway, specifically in the area of Vestfold and Telemark. Well, all of you must be aware that the Volt-Var control has been for many years inside the power system, and there are several devices providing this kind of services like on-load tap changers, shunt capacitor, reactors, synchronous generators, and so on. And the DSO typically use voltage regulators, transformer tap changers, and shunt capacitor for this Volt-Var activity. However, the IEEE 1547 from 2018 make the smart inverter one very attractive solution for providing Volt-Var uh, Volt-Var services. In this case, there are several schemes, controller schemes that can be used. For instance, one of the characteristic could be the reactive power voltage characteristic controller that is represented here in this plot. What we have is a dead band that there is a minimum and maximum voltage and the converter is not producing any kind of reactive power. But if the voltage goes beyond the dead band, there is a slope and this slope will produce or absorb reactive power in order to keep the voltage control. Of course, there is a limit in this control action, and that is the maximum and minimum reactive power that can be provided by the control. However, the QV characteristic is one of the controllers that we are studying here in this uh, in this scientific paper. The other one is the constant voltage control, and that is extremely simple because the converter defines the reactive power output in order to achieve a local voltage at the terminals. And the third controller that we are considering here is what is called the Q-troop control. There is a proportional controller, and the reactive power that is produced by the converter is just a proportion of the voltage deviation from a set point. In this paper, we are using a combination of transmission system and distribution system. The transmission system, in this case, we are using an equivalent model. This is 132, 300, and 420 kV representation of the regional network at the Vestfold and Telemark area. This network has been created using information publicly available, and it includes synchronous machine for representing the hydropower plants available to the loads to the area. Also, the national transmission system 300 and 420 has been modeled as external grids. From the DSO point of view, we are using a radial configuration, 11 kV primary distribution feeder in radial configuration. One of the key features here is that inside this feeder that we have selected for studies, there is something called the Skagerrak net, and this is a installation where they have solar power microgrids, including a battery energy storage. This is like a small microgrid inside the distribution system and a place that we can use for voltage control for the local DSO. The demand in this system has been created using 4 different distribution feeders, combining residential load and the Skagerrak net load. Okay, the analysis that we are performing here, the assessment is based on 24-hour operation. As a consequence, we need load profile for 24 hour. The good news is my colleagues from Loughborough University and at the CRES Research Institution, they have created an amazing model that allow me to create this load profile with a 1 minute resolution. The CREST model is a very interesting model, but it was created for the GB case, and also the model has been recently extended to the Indian case. Here in the University of Southeastern Norway, one of my students, Daniel Petersen, he has enhanced the model by including the variables related the Norway environment. Okay, the Skagerrak net has included a local football stadium, and we have used an ideal load profile of 1,000 kilowatts peak load during the matches. Okay, and then we create this model inside the Excellent Power Factory, including all the factors, including the model of the different feeders and the load and the Skagerrak arena. And here you can see the 24-hour load profile for the total distribution system that we are studying, and there is a total of 22 megawatts, 22 megawatts when we consolidate all the loads. This is the load of one of the subfeeders, okay? And then we have indicators, the performance indicators used in this scientific paper is the energy loss. The energy loss is calculated using the active power losses inside the system. I'm using classical mathematical calculation. It's the area below the curve. There is not much details to add over there. And then we have the voltage difference indicator, and this indicator is related with the lowest voltage level and the highest voltage level during 24-hour period. And here you can see the expression, the equations used for the calculation, okay? Then we have a few scenarios. The scenario one is the base case, and it is considering just the loads, and it's not considering any kind of low carbon technology. Okay, this is used as reference for comparing all the other scenarios. The idea is to see the benefits or negative aspect of including the low carbon technologies. Okay, here you can see this is the 24-hour profile for the grid losses in megawatts, and as you can see, the DSO losses start to change following basically the load profile. Okay, however, the TSO grid losses, they are very small different, slightly different, because there are some other loads considered inside the network. Okay, the scenario number two include the integration of top roof PV systems, and here we have 6 different controllers. We have enabled the PV inverters with 6 different controller, constant power factor, including 1.0, constant power factor 0.95, constant power factor 0.19. Then we have 2 voltage troops, one that we call a slow voltage troop and one that is called fast voltage troop. And finally, we have the ideal case, and that is the constant voltage set to 1 per unit. Over here, you can see the results, numerical results, considering the energy savings in the TSO, and here the energy savings at the DSO. And finally, here we have the total energy savings. As you can see, using the constant voltage set up to 1 per unit is producing only a reduction of 237 kilowatts hour per day. But if we use the slow voltage group, if we use this low voltage group, as you can see over here, we are saving 289.1 kilowatts hour per day. However, something that is very important to see here is that when we are reducing the DSO energy losses, the TSO losses increase, and when we increase the savings on this, we are decreasing on the other side. What I am trying to say is there is an antagonic or diametral behavior. When the energy savings is reducing one side, it's increased on the other side. Okay. Finally, we have here the scenario 3. The scenario 3 is considering the PV, but also including the battery energy system, okay? And in this case, what we are doing is a two-case scenario. In this case, we have subcases that this is the lowest PV losses scenario, and we have the highest PV losses scenario. What I am trying to tell you is that from those cases, considering only the PV integration, we select the two extreme cases in order to assess the performance of the voltage and the energy losses. Okay, this table provide a summary of the different scenarios, considering the high and lower losses. And as you can see over here, the TSO energy losses, they don't change so much compared with the energy losses that they are at the distribution system. The battery energy storage system provides some support for reactive power. However, because the batteries are also providing some active power local production, that has an effect on the voltage profile and the active power losses. Conclusions. Well, in this scientific paper, we take the advantage of the IEEE Standard 1547 from 2018, and we are using the concept of a smart inverter. And in this case, we are exploring the interaction between the transmission system operator and the DSO, considering several Volt-Var controls used for the smart inverters. The interesting thing here is that active energy losses in the DSO and DSO, they are antagonic. I mean, when you try to reduce in one area, the other area increase, and likewise is the same. For that reason, the TSO and DSO must find a balance between the reactive power flow to reduce the energy losses. And that is where the integrated and communicate interaction between the TSO and DSO take place. Finally, after the careful assessment of the whole set of the results, and this paper has many results, we identified that the PV system controller set to voltage drop with 10% and a battery energy storage controller, a constant voltage setup, produce a minimum total losses in this system. Okay. Well, this is all for this paper, and this is time for question and answer. Thank you very much for watching. Thank you very much for your attention.